You know the feeling, right? Stuck in a line, waiting on hold, just sitting in traffic. It feels like such a waste of time. But what if I told you that waiting isn't just annoying, it's a massive hidden cost? And get this, there's a whole science dedicated to understanding it and even fixing it. Let's dive in.
Because that's really what this is all about. What is the true cost of waiting in a line? It's way more than just the minutes ticking by. Waiting has a real, tangible financial cost for businesses, for systems, and yeah, for our own sanity. Today, we're going to unpack that cost and find out about the science behind making lines better.
All right, so here's our game plan. First, we'll talk about the real problem with waiting. Then, we'll get into the costly balancing act that every organization has to deal with. After that, we'll learn the lingo, the language of cues. Then, we'll check out some blueprints for different kinds of lines. And finally, we'll figure out how to find that perfect sweet spot. Okay, so first things first, what exactly is the problem with waiting? Well, for any organization, whether it's a hospital or a factory, a long line isn't a sign that you're popular. It's actually a symptom that you're burning money and making your customers really, really unhappy. And this is where something called queuing theory comes into play. Now, I know it sounds super academic and complicated, but at its heart, it's really just the mathematical study of waiting lines. It gives us the tools to figure out why queues form in the first place, and more importantly, how to manage them, whether we're talking about people, cars, or even data packets flying around the internet. Now, here's where it gets really interesting. The goal isn't to get rid of waiting completely. I mean, that would be crazy expensive. Instead, it's all about a constant financial balancing act, a big trade-off between two costs that are always pushing against each other. Think of it like a seesaw. On one side, you've got the cost of service. That's stuff like salaries for your cashiers or buying more equipment. The more you spend here, the shorter the line gets. But on the other side, you have the cost of waiting. That's the lost productivity, the frustrated customers who just give up and leave. So as you spend more on service, the cost of waiting goes down. And if you cut back on service, the cost of waiting goes way up. The whole game is finding that perfect balance point right in the middle. And this table shows that trade-off perfectly. Let's look at this courier company. They could hire a really cheap team for $500 an hour, but wow, look at that waiting cost, a massive $6,000. Or they could go all out and hire a super efficient team for $4,000 an hour, which cuts the waiting cost way down to $500. But look at that last column, the total cost. The sweet spot, the lowest total cost, is actually that team right in the middle. It's not the cheapest service, and it's not the absolute fastest wait time. It's the best overall balance. So that's the big takeaway here. The whole point of using queuing theory in the real world is to find that perfect, optimal service level that gives you the lowest possible total cost. It's about being smart, not just being fast or cheap. So how do we find that sweet spot? Well, we need a way to measure and talk about any queue. And honestly, it all boils down to just two key variables. Think of it like learning the ABCs of waiting in line. First up, we've got the Greek letter lambda. All this is the arrival rate. It's just a count of how many customers, whether they're people, cars, or emails, are showing up to the queue in a certain amount of time. So for example, if you have 50 cars arriving at a toll booth every hour, your lambda is 50. Simple as that. And to handle all those arrivals, we have mu, another Greek letter. This is your service rate. It tells you how many customers a single server can get through in that same time period, assuming they're working nonstop. So if our toll booth operator can handle 54 cars per hour when they're busy, our mu is 54. Now, for any of this math to work, there are just two basic rules of the game. First, for a line to not just grow forever and ever, the arrival rate, lambda, has to be less than the service rate, mu. You've got to be able to serve people faster than they show up. Makes total sense, right? And second, you have to be measuring both lambda and mu in the same units, so both per hour or both per minute. Okay, so now that we've got lambda and mu in our toolkit, we can start looking at different kinds of queues. Because not all lines are the same, right? So queuing theory uses different models, kind of like different blueprints for different situations. Let's check out two of the most common ones to see how this works. First, you've got the MM1 model. This is your classic blueprint for any system with one server where everything is kind of random and unpredictable. That M stands for Markovian, which is just a fancy word for random. Think about your local coffee shop. You have no idea when the next customer will walk in, and you don't know if they're going to order a quick black coffee or some super complicated latte. That's MM1.
But what happens if the service time isn't random? Well, that brings us to the M/D/1 model. In this case, people still arrive randomly, but the time it takes to serve them is constant and predictable. That D stands for deterministic. The perfect example here is an automatic car wash. Once a car goes in, that machine takes the exact same amount of time every single time.
So why do we even care about this difference? Well, it turns out that predictability is a superpower. As the source material says, systems with constant, predictable service times are just way, way more efficient. But how much more efficient are we talking about? And here it is. This is the big punchline. When you compare the MMM1 model, our unpredictable coffee shop, to the MD1 model, our predictable car wash, you discover something amazing. If they have the same arrival rate and the same average service rate, the average time a person spends just waiting in the line in the predictable system is exactly half. You heard me right, half. You can cut the wait time in half just by making the service time consistent. So let's put all the pieces together. By understanding the costs, by measuring our system with lambda and mu, and by knowing just how powerful predictability is, we can actually start to design and manage systems to find that perfect sweet spot. Honestly, if you remember one thing, remember this number: a 50% reduction in waiting time. It just goes to show that one of the absolute best things you can do to fix a broken system is to attack variability. Standardize your processes, automate what you can, anything to make those service times more consistent. The payoff is just enormous.
So let's wrap this all up. Here are your key takeaways. First, waiting is not free. It has a real financial cost. Second, managing any line is always a trade-off between how much you spend on service and how much your customers lose by waiting. Third, we can actually use simple models to find the best balance. And finally, predictability is your secret weapon. It has the power to cut waiting time in half.
And that brings us to the end, but I want to leave you with a final thought. Think about the worst, most annoying line in your own life. Is it the grocery store, the post office, airport security? Now that you know the basics of queuing theory, how would you fix it? Thanks for watching.